Good evening. This is Dr. Eidelberg, and today's episode is dealing with Gantry thermal lock analysis. We will look at the problem definition. We'll model the system. We'll use Autodesk Nastran in CAD analysis. We draw the conclusions of the analysis, and we'll take a look at the actual industrial solution which was used to solve this problem. We are dealing here with a high-speed surface mount technology machine with a potential for an x-axis lock. This is the x on the right-hand side. This is the x-axis on the left-hand side. This is the y. In each one of these stages, we have linear motors, which is high-speed device, to run the coordinate in x and y direction. The machine carries heavy-duty weight and places surface mount devices on a PCB which runs on a conveyor belt. The heavy-duty mass and the high speed together require very high power to be placed in a linear motor coil, and that power actually generates a lot of heat. When heat is conducted through the beam, then the beam expands, and the expansion, if it reaches high value, could lock the motion of the stages. The picture is taken for Bing Web Research. It's a Juki SMT machine, and our analysis has absolutely nothing to do with the performance of this machine. We see over here also a SMT device which could be actually demonstrated over the internet. We'll see if we have it over here, and we can run it. And you see this is high performance machine that placing in the different chips. We'll come back to our presentation, and we'll define the problem that we have in here by a simple sketch where we have the left axis and right axis. For the x, we have the y beam, and the motor coil generates high power heat generation, and this heat generation causes the aluminum beam to expand, bend, apply forces which could lock the motion of these two slides. The objective of our analysis is to model this phenomena and also design a solution in order to eliminate this problem. So we're using over here the inventor in order to model the cross beam, the Y stage with its slide where the motor coil is located. We use low mesh finite elements. In here we have to define the units for the Nastran in CAD for the linear steady-state heat transfer analysis. And we're using SI, M, K, and second in analysis. This has to be defined. And we also have to define the loads for the thermal analysis. So in this particular case, we assuming in our model that this is the motor coil, and we define the watts per this is for millimeter cube, but the numbers are already set for meter cube, and it's a high number. And we're talking over here about 3-4 kilowatts for a very small space. So this is high energy generator. We also have to define the load of convection, and all the surfaces of the device are actually convecting the heat which is being generated by the coil into the surrounding temperature, and we have to define with the Nastran model the surrounding temperature in degrees Kelvin. We have to also have the convection specification, and we use in the original case a low convection rate and a high expansion rate for the crossbeam. Originally the system was tried out with aluminum, and the heat was actually conducted through the stage and then convected through the surrounding, and the windage effect was relatively low because the exposure of the coil to the wind effect was not very high. We then run the analysis, and what we see is, as expected, when we convert the heat transfer loading, we see that the temperature is high over here at the motor. It's about 86 degrees, and then the thermal deformation over here in this particular case is 3 millimeters. When we look at the reaction forces that the stage causes on the x-axis, we see that it's extremely high, and therefore that solution would not be feasible to run the machine. So the solution that was actually developed at Anurad Corporation by its previous CEO, Anwar Chitayat, who has over 100 international registered patents, US and international, was to take the machine, which was extremely high-speed SMT device, and add a fin to the base of the motor coil, and eliminate the heat concentration not through the windage of the high-speed motion, but actually through a fan. When the machine is stationary, the fan is still evacuating the heat. There also was a change of the beam material from aluminum to ceramic with a very low thermal expansion coefficient. We're talking about 1 part per million versus 24 parts per million for aluminum. And in addition, adding a thermal expansion joint such that if there is a minuscule expansion, then the thermal expansion joint will give, and then will not cause any locking forces on the X stage. This completes our presentation for this evening, and what we will do in our upcoming lab experiment is to actually design the fins and the thermal expansion node, and changing the material to the ceramic in order to simulate what Anwar Chitayat has developed about 20 years ago at Anurad. Thank you.